Hello, everyone. This is Deep Learning Classics and Trends. And today here we have Gargi telling us about this paper that she decided to present. I don't know, what was your selection criteria? And you can tell us more about it.
Sure. Yep. Thanks, Roseanne. Thanks for conducting this wonderful reading group, and thanks for having me here. Hi, everyone. I am Gargi Balasubramaniam. Currently, I'm a master's student at UIUC, and I am not a researcher in natural language processing or language models. I just do research in general, reliable machine learning and how you can make models trustworthy, robust. So I chose this survey paper because I feel like it touches upon most of the recent developments in making language models more aligned with the output that one would expect them to do, especially for more complicated tasks, which I'll be also talking about through the talk. So today, my agenda is that at the end of this talk, all of us are aware of the common buzzwords and terms which people are using these days to, deal with language models. And I want this to be an interactive discussion. So please feel free to jump in with questions or any thoughts in general you have, because a lot of this is just, free floating right now. People make claims and it shows nice results, but we need to ground all of it together to really know what might work and what might not in a new scenario. So let's first get a quick review of, there's something on the chat. Okay. So let's first quickly review, what language models are. And I've taken, multiple slides from Jason Bay's recent talk on emergence. So I'll share this set of slides with Roseanne, and you guys can check all the sources I've used here. So if you look at a language model, what it essentially does is, given an input or a prompt, it will give you a probability vector of all possible words that can appear next. So this language model was trained to do next word prediction, and it's trying to minimize this loss, which maximizes the plausibility of seeing the right kind of words once I already observe a prompt, right? So the input here is you would like to maximize the context in your input in order to give maximum context to your language model, and you hope that the language model will produce plausible and sensible natural language outputs in response to your input prompts. Now, if we go one step further, this is just a statistical language model right now. And one might ask, why do I even want to augment language models in the first place? Like, why is this an important problem to address? So does anyone have any, first thoughts, or, why am I even reading this paper or talking about this? Would anyone like to pitch in or put something on the chat?
One thing might be, I think they were trained up to 2021, so you could access newer data, things like that.
Okay, that's a very good point. So being updated with the latest and factually correct information, that's one aspect. Any others?
You might want to depending on the person you are interacting with the model, you want to change the model aspects or certain aspects of the model to make them feel comfortable with talking to that model.
I see. So contextually appropriate outputs. Is that what you mean?
Yeah, even depending on how the person who the model is talking to.
Right. Okay. Makes sense. So steerability in some sense. And let's see, factual, truthful. I see a couple of answers on the chat. And yeah, most of them are, going towards the right direction. But one thing which no one mentioned yet, someone mentioned tools. But one thing is that language models may produce some outputs based on statistical patterns observed during training across the large scale of data. But are these ways of generation plausible? And when I say plausible, is it aligned with how humans might want a language model to reason about certain kind of tasks, right? So we are addressing this question of reasonable generation of text by language models. So remember that a single language model can only do so much, right? It's just a single parametric model trained on a large scale of data to predict some next tokens, with great accuracy, and it sees limited context, right? So what are the kind of tasks we might want it to perform well on, given that they are becoming so advanced and we have the compute to train such large language models? So Jason talks about the set of tasks which can apparently be solved by language models pretty well. So a few examples include like learning appropriate grammar, learning the lexical semantics, or having, certain knowledge of the world facts, doing sentiment analysis of various kinds, and doing also translation. So the last two rows in this table refer to spatial reasoning and like math reasoning. So you can imagine that after having seen a large number of possibly educational content, a language model may have picked up correlations based on how certain problems are solved. And when I say problems, these could be like natural language problems, math problems. And the claim here is that these language models can already do some rudimentary arithmetic and spatial reasoning tasks, although these are inherently not natural language tasks, right? So they may have picked up some notion of or some reasoning regarding these tasks, which are generally seen a lot during training, may have been seen. And where is the gap to be filled? Well, one gap is definitely, being factually correct. So someone mentioned being updated with the latest knowledge, which is interesting. But another thing which people have started expecting these days is how plausibly do you reason about new tasks or solving new things, which may require going beyond just the language, such as reasoning about, the 19th digit of pi and doing things with it, or handling extremely long inputs or long contexts. So in this talk, we will mainly focus on the second and the third row, which is how do you solve tough arithmetic problems, tough question answering, common sense reasoning problems? So how do you make language models generate output not only correctly, but also plausibly? So this set of tasks, which we would like to perform well on, gives us certain idea about the desired behavior. So today, in this from this survey, I will pick up three aspects which include reasoning and combining reasoning with the usage of tools, and finally, leveraging external data sources to augment the knowledge of a language model. So recall that with these set of tools, what we're doing is we're expanding the context of a language model cleverly. So there are many ways to expand this context. And you are also possibly leveraging tools which are not parametric. So they cannot be possibly learned along with your general learning process. But at the heart of reasoning and this entire line of work is clever context expansion. How can I expand the context of my language model in the best possible manner? And what are the different ways of doing it? And how does it empirically manifest in the variety of models and the scale of models which are present today? So we'll be briefly touching upon these three pillars of augmenting language models with both tools, which may be non-parametric, and with a greater context in general. So I'll pause here and I'll open up to the audience for the following question. So this is a disclaimer before we do talk about anything in the rest of the talk. What comes to your mind when you think of reasoning in the context of language model? Do you think reasoning is even possible? Like, do you think language models can know what 2 + 3 or 5 - 5 means? I just want to know what everyone thinks.
I feel like when I think of reasoning, it's sort of like a show you're working type thing. So like there will be a set of steps that kind of explain it. Whether the model understands, in quotes, I don't think so. But like if it's, I guess I'm kind of doing the Chinese room experiment thing here. Like if it's walks and talks like a reasoning agent, then I suppose it is sort of thing.
Nice. Okay. Anyone else?
Yeah, I mean, if whether or not model actually thinks or understand is completely irrelevant, as long as it appears to think or understand and it can do our job like well enough. Like who cares if it actually thinks or understands?
Right, right. So agreed, like both of you raise valid points. When we say reasoning, definitely we are making or enforcing some sort of prior on the kind of output we exist and why we want it to exist. But the way we scope reasoning for the rest of this talk and in general in this context is that reasoning is when you want to allow the language model to reason for the right reasons, meaning you decompose the task into simpler subtasks and you solve those legitimately to obtain a correct answer. So someone here mentions the correct thing, like it's breaking down problems, and someone also mentions they are good at basic reasoning, but they are poor at compositional reasoning. So yeah, the word compositional reasoning is a very nice one, that we can break down a broader task into simpler subtasks and allow the language model to solve each of these subtasks with good accuracy, legitimately, with high certainty, and then hope that the composition of the answers from each of these subtasks will give us the overall right answer for the right reasons. And it's a very intuitive thing to imagine that would happen. But someone may just, counter you saying that all you're doing is you're increasing the context to, correctly predict the missing token. Well, yes, that's indeed true. And there's nothing more we can say about reasoning in this, in this setup. But nevertheless, it's good to keep in mind that for the rest of this paper, reasoning simply means decomposing the entire task into simpler subtasks and composing them back in a legitimate manner. Okay. So I should also, drive across this point, which is my opinion on this entire, area of work, which is the relation of the augmenting tools with the scale of the model. So here I've just, taken the most recent large models which have been used. Not all of them are large per se, but if you look at the most common ones, which are, in talks these days, then you can look at the PaLM model by Google, which is the biggest one here. It's 540 billion parameters. And then you have like GPT. GPT is 175 billion, GPT-3. And then we also have Gopher by DeepMind, which is like 280 billion. So you should keep these numbers in mind because we'll be referencing to these models a lot more in the rest of the talk. So have a vague idea that, okay, when I say small or a normal language model, it means like 1 billion parameters, 7 billion parameters. So something like a GPT-J or a GPT-Neo will count as that. But when I say large models, I typically refer to models like PaLM, which are at like the order of hundreds of billions of parameters. So make sure that you have this numerical idea in your mind. And also, like you must have heard of this word scaling and scaling laws for language models. Just know that scaling simply means that we are measuring or evaluating the capability of a language model based on the compute which was required to train this language model. So I've just shown a few parameters here in this picture. But you should remember that the story doesn't end here. As we'll see in the later slides, when you increase the scale of a model, a lot more nonlinear things happen, which you would not otherwise predict. So keep in mind that, a small model is 1 billion, 10 billion, while a large model is like on the order of hundreds of billions. So, and I also want to touch upon this concept of emergence, which, is also something which all of us should be at least aware of by now, that emergence is, emergence literally is the meaning as the word suggests, that as you increase the scale of the language model, there are some capabilities which non-linearly appear when the scale is very high. And this was, corroborated with empirical results from a recent paper. which says that on a lot of tasks, the accuracy via prompting suddenly, goes up a lot if I enter the regime of like 100 billion parameter models. So something more is happening here, which is not really explained by the equations or the numbers that we saw earlier. So we should keep this in mind that when you're augmenting language models, you should not only think about the methods, but also think about what is the scale of the language models that you are trying to augment. So I see a couple of comments on the chat, and let me just go through them. Okay, so I'll finish the part on reasoning, and then we can come back to the set of questions and have a discussion. So if the concept of emergence is clear, let me go on to the next slide, which is interesting. So remember that we were claiming that emergence leads to very nice performance gains. And as you increase your model size, you are getting very nice accuracy. But the story is not that straightforward. There's a recent work which says that as you increase the size of your model might have emergent capabilities, but there's also an emergent compositionality gap. What does that mean? So the authors in this work conduct a very simple experiment. They take two questions. So you can have like questions, factual questions, like when was Justin Bieber born? And who was the champion of the following tournament, right? So these are two single questions, but when you combine them, when you compose these two questions, you might want to ask, who was the champion of the Masters tournament in the year that Justin Bieber was born? So this requires decomposing this big task into two smaller tasks and then correctly answering each one of them and then combining the answer back together in some way to give the correct answer, right? So it was found that not only does the emergence of capabilities increase, but the compositionality gap also increases with scale. This implies that larger models might be very accurate, sure, but it looks like they are not really reasoning for the right kind of reasons. So this compositionality gap is still existent, and in fact, it's increasing as we increase the scale. So this implies that maybe we are not really, maybe there's much more to be done, given that this gap is pretty evident, especially in the large language model regime. So keeping this in mind today, I want you all to know that whenever I mention any method, you should think about how this scales with the size of the model that I'm training on. So this is an aspect which is not covered in the survey paper, but this is something which I found when I was reading through the paper, that different kind of strategies work for different scales of models, right? So if you look at the very large, large model regime in the order of hundreds of billions, things like few-shot reasoning, which we'll talk about, few-shot reasoning, few-shot prompting, they seem to work well enough to like fix the reasoning behaviors that we want to see. But this unfortunately does not improve the performance for smaller language models, where one might have to further augment the context with external tools, external databases. So there's this spectrum across the size of language models, as you can imagine, where for larger models, reasoning and like very nice prompting tricks seem to work just well. But as you keep on decreasing the model size, which is something which we all can do realistically, we might have to combine this reasoning aspect with tools and, retrieval-based methods. So just have this notion of grounding yourself with the scale of the language model when you read these papers. I think that's really beneficial in understanding what works in what case. So now that we have this, let's go on to the first ingredient to the magic potion of coming up with the best language model, which is reasoning. So I'll begin with chain of thought prompting, but let me take a pause here to see if anyone has any questions. Would anyone like to, say something, make any statements? Okay, I assume the answer is no. So let's go ahead.
I did have one thing actually, sorry, just before you move on. So is what you were implying that like the tool usage is harder to do with larger language models, or that it's just more it's more necessary in a smaller model because the large models
The
can
latter
do
one.
reason?
That's a good question. That's a great question. So when I plot this diagram, in my annotation, I imply that in order to improve the reasoning capabilities of smaller models, one might need to resort to things like augmenting with tools and databases, because prompting or few shot techniques, which work well for larger models, may not transfer well to smaller models. And we will see that as we go forward. But that's a great question. Thanks for bringing that up. Yeah. Cool. So this paper is, I think, like everyone must have heard of, seen this paper in some shape or form. And the idea is very simple. So to give context, we have a language model. Say you have a language model and you are allowed to give it some prompts. We are not doing any fine tuning. So another point to keep in mind for the next few works, like I am not mentioning any fine tuning till now. So we are only in the regime of prompting, where we are allowed to give a set of prompts to the language model and we assess the output of that language model. So this work is the first, like one of the first works to introduce like chain of thought prompting, and that's very suggestive and intuitive. So by using few shot demonstrations, where few shot refers to the facts that you can use a limited number of prompts to show that, hey, this is the expected output. And then you finally ask the model, what's the final output? So you can expect that the model will expand its context in a way in which you asked it to expand it and give you the right answer for the right reason. So that's exactly what is happening here. The blue, so the authors here, inject all of these prompts with a thought, a chain of thought, which is how one might have arrived at a certain answer. And by using this, demonstration or exemplar, as they call it, you can teach the model to reason via a chain of thought. So chain of thought, or COT, is very straightforward. I have K set of demonstrations, and K was chosen to be 8. So you have 8 demonstrations which you give to a language model. And for every demonstration, instead of just having the input and the output, you append it or you intersperse it with the reasoning for every question and answer. And then you expect that the model hopefully makes a correct prediction. So this kind of chain of thought prompting is explored across data sets involving arithmetic reasoning, common sense reasoning, and symbolic reasoning. So in arithmetic reasoning, you will have to do literally like mathematics. In common sense reasoning, you have to, reason about like common sense facts and, things which can happen, things which can't happen. And in symbolic reasoning, this is very interesting. So you might be asked to do things like take the last letters of these two words and concatenate them together. So these are the array of tasks which are considered for the purpose of this work. And it's shown that when you increase the size of your model, right? So as soon as you reach the large language regime of the order of hundreds of billions, this chain of thought prompting evidently improves the performance of your model. So let's just look at one of these graphs on the left-hand side. You can see that as you increase the model scale, so let's say we take the PALM model at 540 billion parameters, it in fact even surpasses the previously, found supervised best model on this benchmark called GSM-8K, which implies that with increasing model scale, you are unlocking certain emergent capabilities by leveraging this chain of thought prompting. And the marginal benefits of chain of thought prompting are much more evident when I have a large scale model. So in the low parameter regime, it was found that sometimes chain of thought prompting even hurts. So for example, for Lambda on this GSM-8K, you can see that chain of thought prompting actually performs worse. And we'll discuss some reasons for why that might be happening. But the takeaway from this entire set of graphs is that chain of thought prompting typically materializes well when you have a large number of model parameters. And one task which I want you to keep in mind, which we'll get back to, is the one highlighted in blue, where during training time, you are asked to take the last two letters and concatenate them. But during testing time, they do an OOD evaluation where instead of 2 characters, you are now asked to append 4 characters. So it's going one step ahead and requiring the model to have an understanding of last X characters of a word, right? So we'll come back to this task later. So keep that in mind. But for now, you can simply, what you can take away is that, okay, if I have a very large model, I'm pretty well off with just, employing a few short chain of thought prompting, and I should observe the benefits, even comparable to a supervised model, which was fine-tuned explicitly for that particular downstream task. So while this might seem very straightforward, you should sit down with this and think of how in-context learning, as they say, with just a few demonstrations can really benefit, in the regime of large language models, right? And another interesting thing, which I'm sure many of you must have wondered, is that how robust is your model to the different choices of prompts, right? Because prompt engineering is kind of like art. And you might want to imagine that I write certain chain of thoughts. What if fellow coworker writes another chain of thought, right? So you can have different annotators. And then you can even have, model chains of thoughts, which are directly provided by the data set. So experiments were also performed, across these different annotators and different styles of formulating the chain of thought. And it was found that in any case, the solve rate is pretty invariant to this choice, and it definitely outperforms standard prompting. Although there is still dependence on, the annotators which did it. So on the left-hand side, you can see that there's quite a significant difference in the solve rate amongst different annotators. So prompt engineering definitely matters, but it for sure improves performance over your baseline method of standard prompting, which is interesting. So I feel like this robustness study is something which should be more widely incorporated in all of the other works. And if you're writing a paper right now on language models, make sure that you also try to evaluate the generality of your model on these different kinds of chains of thought. And now let's go on to thinking, why is it only that it happens on a larger scale, right? So why is it that small language models cannot even benefit from this kind of demonstration? Well, it so happens that it was found out during evaluation that even simple arithmetic operations are hard to learn when you have small language models. And some get stuck in infinite loops or do not even arrive at an answer which can be parsed in this case. So it looks like, so when you scale from a smaller model to a larger model, a lot of errors are fixed. And this has to do, A, with the emergent capabilities of models, B, with the fact that few shot prompting, chain of thought prompting is more beneficial for large models. So this is a complicated recipe of the model size, of the model prompts, and no one knows why this happens. But nevertheless, you should keep in mind that chain of thought prompting does not work for small models. So if you are, deploying a 7 billion, 7B model, do not think of using chain of thought prompting, at least be wary or be cautious. So you might think, okay, we did few short demonstrations. What if I just do 0 shot demonstrations? And when I say 0 shot, I mean, I'll just, trigger the model to reason in some sense. And that's literally what the authors do. So you can just ask the model to think step by step, right? So you prepend the prompt by saying, let's think step by step. So surprisingly, this works very well. And if we look at, what is the exact procedure they follow, they add this key phrase called let's think step by step, and then arrive at the final answer in 2 stages. So again, remarkably, when you, the evident benefits of, chain of thought prompting with two-step reasoning are much more evident when you, again, increase the scale of your model, similar to the observations in the previous work. But to me, what's more interesting is the kind of mistakes which these two paradigms make. So at the face of it, you will imagine that zero shot versus few shot should not make a lot of difference. But it so turns out that even within the kind of mistakes that are made, few shot prompting is making a lot of calculation errors, while zero shot prompting is pretty good at that. So this just forces one to think whether providing demonstrations in the first place is a good idea or not. And, it opens up possibilities for doing chain of thought prompting, but with different tunable prompts in some sense. But for now, it's interesting to know that both these paradigms make different kind of errors. And even in spite of having more demonstrations, few shot COT has higher error rates in, common sense mistakes. So these are some aspects which you should think about and probably incorporate in your, way of prompting. And another interesting evaluation from this work is the kind of prompt that you use. So you would imagine that we can have different variety of English phrases to prompt our model. So they found out that let's think step by step, full stop, achieves the greatest accuracy amongst all other possible kind of prompts. And what I take away from this table is just the steerability of language models in the zero shot regime. So you can even mislead a language model by, saying irrelevant things or, asking it to do the wrong things. But it's remarkable to see the dramatic change in accuracies just based on the kind of input prompts that we use. So really, like, context expansion involves a lot more, details which you should empirically evaluate. And this is an interesting, hyperparameter search landscape, which opens up nice directions for future work as to what makes a good zero shot prompt. And finally, like, going along, the third basics, which everyone should know of, is self-consistency. So we talked about, doing chain of thought with few shots or without any demonstrations at all. But can I go a step further and again incorporate the intuition that I have multiple reasoning paths, and based on these reasoning paths, let me take the common consensus. So it's like you're forcing someone to think about a problem in n different ways, and then taking a consensus from those n different ways to produce the final answer. And how do you translate it in technical terms? While sampling the probabilities, you just scale the probabilities with a certain temperature so that you can sample more diverse outputs. So you just choose a higher temperature while sampling, and then you find that sampling from a diverse set of reasoning paths, as they call it, can help you get a better answer. So you should note that chain of thought prompting, adding trigger words, and doing self-consistent reasoning, these are the three basic methods which you can combine with literally anything, which we'll discuss after this. So these are kind of the baselines for improving the performance of your language models. And I'll take a pause here. Does anyone have any questions, comments? Okay.
So one comment on that, Gargi, was about the definition of reasoning in this context, right? Like they are utilizing decomposability as the main, right? If the model can identify its components and then decompose the problem more effectively. Do you come across situations in which, the composability is not just the only dimension where, but model is perhaps inaccurate in other ways?
For this paper, no. Reasoning simply means, in English, natural language. So remember, we have a natural language model. We have only certain ways to operate with it in a human interpretable manner. So to you, if I ask you, how do you do this? You will have a set of smaller sentences which correspond to smaller problems, which you will then combine the answers for and get the final output. So no, for the scope of this work, this paper, and generally these works, reasoning is only considered to be by accurately solving subtasks and combining them together to come up with the final answer.
This is not a question, but the chain of thought thing reminds me of the instincts versus search dichotomy, right? In the reinforcement learning, there is like you can either train the model to give search in all the possible space to find an answer, or you can like ask it to few shot the answer, like just give me answer 0.1 second, or you can just give them a lot of time and ask the model to search using the time. The chain of thought thing is like searching through this reasoning space, while simply asking it to answer directly is like asking it to instinct the answer.
Right. I think what you're saying is interesting, and it can be, so I can reiterate what you just said. So you're essentially saying that we are, by doing this chain of thought, we are enforcing a expansion of the space from which the model can do next word prediction, right? And when you expand this possible space from which next word prediction is being done, you would hope that this context expansion leads to a more accurate answer.
Yeah, basically making it use the time it has.
Right. So I'm not sure what time exactly means here, but
I mean, simply that it will take a large amount of inference time to make those do the reasoning chain, right? But if you are like asking it to give an answer 2 + 2 what, it's giving you instantly like 1 token to few tokens, right? So even if it has time, it's not using it. Even if you give it like an hour to like think about what will be this answer to the arithmetic problem, it is not using that time. By forcing it to do chain of thought, it's actually using the resources it's provided. For example, similar to how in RL, you force the model to search through the space instead of giving the answers.
Right. Yeah, that's an interesting point, because I have never considered, the time aspect here, because we're talking about operations which happen pretty instantly. But I'm happy to take that up offline or after the talk. And I just did a quick time check. We're pretty much into the time, so I'll kind of rush through so that we can go through the set of all possible things that people are doing. So with self-consistency, another like an interesting experiment which I found was that when you do greedy decode simply means that you choose the most probable answer with a very low temperature, versus when you sample multiple reasoning paths and then you choose the most consistent answer. So if you observe all of these curves, there is a certain trend of diminishing returns which is observed, which is nice. So this curve could be increasing in any manner, right? So it could be also increasing linearly for all you know. But it so happens that as I keep on sampling more and more reasoning paths, beyond a point, adding more paths doesn't really make sense, because you kind of run out of the reasons that you have for a given answer. And I feel that's very human aligned, because that's what I would expect when I'm doing reasoning and you keep on asking me for more and more ways to reason. I will give up at some point because I have no more new information to add with the reasoning part. So this is interesting because it tells us that with the submodularity that we observe, only with a certain set of reason paths we can get a guarantee on the performance with respect to the size of that set. So this diminishing returns property is very interesting to me. And that's something which I wanted to mention. And finally, chain of thought prompting is also benchmarked on the Big Bench dataset. So many of you might have heard of the Big Bench dataset, where we have a set of many different tasks. And out of these, there are 23 very challenging tasks in Big Bench hard. And it was demonstrated that when you just apply chain of thought prompting to this codex model, the average delta with respect to the human rater significantly improves, which implies that, okay, chain of thought prompting indeed helps. So another one of like an interesting diagram is to see that, okay, we have some emergent capabilities, but you're further, by leveraging chain of thought prompting, you are expanding the set of possibilities, especially in the large regime. So this just drives home the point that I've been mentioning till now, like bigger models, emergent capabilities, and more possibilities by leveraging simple chain of thought prompting. But there's a plot twist. So just yesterday, there was a paper from people at UW Maryland, which talks about how chain of thought prompting may not always be effective for models like ChatGPT versus GPT. So I would urge you all to like check out this thread and this paper in general, because it's interesting. It says that for ChatGPT style of models, which are trained with, which have some component of reinforcement learning and instruction tuning, where you're not freezing the baseline model, chain of thought prompting may not always improve performance and can actually degrade performance. So that's pretty interesting. And I would definitely recommend going through this thread, because I myself didn't have the time yesterday. And another like set of, cool strategies. So there's a paper which talks about how you can teach a language model to decompose the problem, right? So earlier, we were decomposing the problem ourselves and showing the demonstration, but let the language model do that as well, and let it decompose the problem and keep on answering its own questions. So you allow the model to decompose the problem and determine the follow-up questions that would be required to come up with an answer. And it was found that this kind of least to most prompting really helps. So if you remember the letter concatenation task, which I had mentioned a few slides back, they show that they're able to generalize very well, especially to an arbitrarily long, length of letters which you need to concatenate. So you can see that chain of thought prompting really degrades when you have a very large sequence, but this works pretty well for least to most prompting. I don't know why this, works very well beyond chain of thought, and there may be certain tasks for which specifically least to most works pretty well, but nevertheless, it's an interesting technique to know of. And two more models which you guys should know about. First is Minerva. So Minerva is fine-tuned on a set of scientific papers, which involves both archive data and math web pages. And this was essentially the PALM model plus, which was fine-tuned on another data set consisting of these scientific papers. And it was found that it can do pretty concise and terse mathematical reasoning. So this is another flavor of reasoning, not exactly like the previous ones that we have seen, but reasoning by literally asking the model to check out reasoning papers and papers which build upon reasoning, and then learn from that information. And similar to this was Galactica, which was a model released by Meta last year. So here, the step-by-step reasoning is manually injected into during the pre-training phase inside these work tokens. And at inference time, you can simply trigger the reasoning by leveraging the work token. So again, like you should just know that reasoning can involve chain of thought prompting, various kinds of it, or you can fine-tune your model on reasoning specific data like Minerva and Galactica. And all of this work originally came from this, intuition provided by Scratchpad, which literally means that you're asking a model to have a scratchpad of the set of states and the corresponding actions that are maintained throughout the code. So this was specific only to code. And Scratchpad showed that by maintaining this execution trace line by line, you can greatly improve the accuracy of your model. So ending this set of prompting techniques, we have algorithmic prompting. So it tries to combine all of the methods that we saw previously in some form by ticking off most of the boxes of how well you would like a model to generalize. And just to give you an example, if in Scratchpad, we just maintain a set of pairs, the states of a program. And in chain of thought, we rely more on natural language to give the chain of thought. But in algorithmic prompting, we kind of combine these notions and, do something like you literally unravel an algorithm and talk out your code like you're in an interview, and then provide it to the model. So with this algorithmic prompt, it has been found that the reasoning capabilities of a model are improved. So again, this is another flavor of reasoning which leverages, inspiration from code for the final output. So let's now go to access tools. So we talked about some basic, bread and butter of reasoning. And can we combine these reasoning techniques with access to tools which the model can use to augment its language? Well, yes. So the basic idea is, so I'll start with this basic paper on how you can augment LMs with data from the internet. So it's very simple. You take the question and you ask Google search to return a set of answers for that question. And for whatever documents you obtain from the top 20 URLs, you parse them into paragraphs and rank those paragraphs based on some TF-IDF based scoring. So all we're doing is we're just searching the query on the internet, getting the top 20 responses and parsing them into paragraphs. Now, once we have every paragraph, there is a way to find the probability of an answer with a given query by using these paragraphs. So the probabilities which I've just shown here are ways of combining the probabilities from the TF-IDF scoring and the probability of the language model. So if you notice here, the inference time is kind of going up because you're taking time to compute all of these probabilities. And whenever you see RAG, I would urge you to keep this in mind, that RAG stands for Retrieval Augmented Generation, and it's a way of combining the TF-IDF probabilities with the language model probabilities. So either you could compute this sum, which takes an average score across all paragraphs, or you could maximize this probability by expanding it using the Bayes rule. And you can combine both of these, which what they refer to as POE. So they show that, so here, CB stands for closed book and OB stands for open book. And re-ranking is where you're ranking answers based on the probabilities that were just mentioned. So you can observe that with the state-of-the-art performance mentioned here, by simply having access to the internet on this Gopher model, you can, try to reach closer to the state-of-the-art. And I think the main interesting point in this paper is the following, which brings me back to my scaling point, that even 1 billion models are able, even 1 billion size models are able to achieve better performance over 280 billion models by having access to the internet. So if you look at this diagram, so instead of increase the amount of training parameters, we increase the inference time by, doing the retrieval, computing probabilities, and we find that, say, POE with 7 billion, like you can see the green dotted line, outperforms the CB for 280 billion, which is the black dotted line which you see here. So CB stands for closed book. So very interestingly, you can surpass, a 200 times bigger language model by simply searching the internet and cleverly using the queries retrieved, augment your knowledge, and then do inference. So this just shows that for smaller size of models, resorting to augmenting tools and using the internet, for example, is a nice way to is to cover up for the gap which you lose out on by not benefiting from simple chain of thought prompting. So it's a very interesting fact to me, and you should also keep this in mind. And another interesting direction is to know how to learn to search for the right kind of queries instead of just pasting the question as is. So Self-Ask, which is also a nice paper, I would highly recommend you read it. It does similar kind of like prompting, but in every step, it allows itself to ask a follow-up question to itself, access a search engine, and then append the response for the next follow-up. So you let the model decide when it wants to stop, what are the follow-up questions it wants to ask, by doing a few number of demonstrations. And what's interesting is that this kind of internet-based retrieval is able to close the compositionality gap, which we just mentioned a while back, which is pretty interesting. So at the heart of it, all it is prompt modification, but you can access the internet in the middle, combine those probabilities in certain ways, like we saw earlier, especially for smaller models. So here we can see that the compositionality gap also reduces even for larger models, which is good news. And on similar lines, if you combine the ability to reason as well as act, which is search on the internet, another way to combine these methods is to do some sort of question answering, but you allow yourself to process a question, conduct a chain of thought reasoning, but then also act. So it combines what we saw earlier. It combines chain of thought reasoning and it combines searching the web in the following way. So here's a sample demonstration prompt, which is seen here. So as soon as you see action 1, you literally execute that action based on the tools available. And it's shown that across scales, the benefit is more evident only for larger models. So again, very interesting phenomenon that in spite of augmenting, allowing access to the internet, somehow for smaller models, the performance is not very good if you use the React method. And this might force you to think, am I expecting too much out of the model as soon as I ask it to reason about the actions that it just, completed. So here, like we saw how you can use search engines to do so. And this one, which is my personal favorite, is, having access to code, right? So let's not think in terms of English, but let's think in terms of code. Also because your models are trained on a lot of GitHub data. So they have access to a lot of code data, which was present on the internet. So by having access to a Python interpreter, you can think in terms of code and then just execute that program to return the answer. And it turns out that this method does very well. So every prompt here is a set of interspersed English language commands as well as the corresponding Python codes. And it turns out that, doing this kind of program-aided language modeling, you can really improve on all the code models that are previously existing. And it also works on top of text models, provided they are, good beyond a point. So for example, for the first one, it doesn't really work well. And it also is interesting to know that clean code matters, because if you remove like variable names and comments from the code and then do this kind of programming aided language modeling, the performance indeed decreases. So it means that not only should it be code, it should be clean code, which is well labeled and well readable, which also is interesting to see that by having access to a readable code, you can obtain better performance on your natural language tasks, which involves some amount of reasoning. And it also works with the least to most prompting, which we just saw earlier. So it's not just with the chain of thought reasoning that we saw. So just to like wrap it up, here we have a comparison of different models and the different kind of techniques they use and the different tools they have access to. And the takeaway here is that as soon as you condition on code, the improvement on math tasks really increases, which is nice to know. And this is probably because your baseline models are exposed to a lot of code, which is possibly present on, say, GitHub. And that allows them to leverage that signal in the expansion of your context. So I find this phenomenon pretty exciting. And just mentioning, like, instead of Python, you can invoke another kind of simulator, say the physics simulator, and perform well on tasks which involve physical reasoning or reasoning about how must the physical attributes vary. So you can have literally access to any form of interpreter which is suited to your specific task and augment your language model with that. Finally, we have Toolformer, which is a very recent development, literally this year. So what Toolformer does is it learns to use the tools. So you don't even need to tell it what tools to use. You just give it access to some sort of tools. So what it does is it creates corresponding API calls, which are candidates, and you sample certain API calls, you execute them, and you only include the response from those API calls, which will probably help in predicting the next token, right? So just going into more detail, you show it certain kind of prompts like this. So in the input that we provide, we say that you can use the calculator or the wiki search or the the question answering database to evaluate all of these. And based on this, it learns to intersperse the text with certain kind of API calls, actually execute those API calls, and then decide whether or not to use the API call or not. So it's kind of search mixed with, few shard prompting to come up with, how to use tools. And here the nice thing is that you can scale it to many kind of tools. So that's a very interesting aspect here. And finally, I'll not go into too much detail for retrieval because this involves like a lot more nuances. So IRCOT, which is, of course, chain of thought with information retrieval, is one example where what you're doing is you're generating the next chain of thought for yourself based on the documents that you have seen previously. So all the questions that you have seen previously, as well as the evidence that you have seen, goes into creating the next chain of thought for your own reasoning. So till now, the theme we have seen is that you can intersperse reasoning, chain of reasoning with access to search, access to retrieval, combining those probabilities, and come up with a very nice combinatorial number of ways to go about the task of solving mathematical reasoning, question answer reasoning, and symbolic reasoning. So I won't delve too much into this, and I highly recommend this paper which came out this week from UIUC as well. So this talks about what kind should you even pre-train autoregressive language models with retrieval. So it's a whole branch of study in itself, and I'd highly recommend having a look at this paper. And I'd like to conclude because we're almost at time. The takeaways which I hope you took away from this talk is that chain of thought prompting can in general be viewed as a context expansion technique, which you can use in conjunction and compose with other techniques. And code conditioning surprisingly provides very important and useful signals. And code conditioning has not been explored in the context of small models, at least as much as I am aware of, and I'm wondering why. And I believe code conditioning, even for small models, should help improve performance. And finally, you can, especially for smaller models, you can ask the internet or like Wikipedia and combine it with your own thought process to act and retrieve the right kind of information to arrive at the correct answer. So finally, before I end, you should also think about, the ethical considerations of what you're doing. So there's this work which says that do not think step by step, because the moment you do so, you uncover a lot of, bias or toxicity that is uncovered in the training data. And this paper consists of a lot of examples of such, toxic or dangerous chain of thoughts, which should not be appearing. So while it's related to, controlling toxicity in general for language models, I feel, like whenever we introduce such an approach, it's important to think of the ethical impacts of, such approaches. And I think this paper is a interesting empirical exploration of how chain of thought might affect the efficacy of language models in producing good output, which is not dangerous. So I'd like to conclude my talk with this tweet from Miles from OpenAI, which says that LMs++, I like that name, LMs++ will take years to fully settle, but till then, no one knows what's going on. And I hope that by this talk, you have a fair idea of what might be going on. And I'm happy to have any more discussion. And thank you.
Thank you, Gargi. You promised one paper, but you end up reviewing 15 papers.
Yeah.
Very generous. Any questions, discussions?
So if I have a 1 to 2 billion parameter model, is the most effective thing with those, would that be something like Toolformer, or like that would be effective? So I can't really go up into the chain of thought stuff, but allowing it to learn like which API calls to make, etc., is the best thing to do?
I would recommend not adding complicated like thoughts of reasoning. So in Toolformer, you still have to reason about the kind. Okay, wait. I think you are right. Yes, the authors don't experiment on small models, so I'm not aware of how Toolformer works for small models. If I were you, I will start with search-based models, which simply search and append the answer to the prompt without constructing any chain of thought for that specific action. And if that doesn't, seem to match the accuracy, and if I have a lot of tools, like in your case, then Toolformer might be a good idea. Because another distinction is that in Toolformer, we have quite a few tools which we have access to, and it might be useful in that case. So yeah, you raise a great point. But if I were you, I will stick to simple search, say 1 or 2 sources of search, and see if that solves my task.
That makes sense, actually, because I was a little bit confused by Toolformer, because it seems like basically when you were explaining the self-consistency thing where you'd have multiple reasoning paths and then you pick like the most probable few, that essentially seems like what Toolformer is, but just for API calls instead of just prompts. And so that was why I was thinking, like, so it does need like a large model for it to still be effective, because it's essentially still chain of thought. It's just for like a different sort of purpose, if you know what I mean. Like it's still kind of
right. So you're saying like let's do like self-consistency with API calls in some sense, like
yeah, essentially. I mean, that's what it seems like to me. I haven't read the paper, so I'm not too sure. But just from the outside looking in. But okay, no, cool. Thank you a lot for the talk as well. That was great.
Thank you. Yeah, great question. And I see a question. So I'll definitely share the slide deck with Roseanne, and I'll add all the sources which I've referred to here. So that should help everyone. And there's a question which says, how do you think the expanding the context windows will help, given the fact that smaller models augmented with retrieval do better? So are you talking about expanding context windows specifically for smaller models? I didn't get the question.
Yeah, that's what I was asking.
Okay, so I feel that there are ways of expanding context, and one way is to expand it via chain of thought prompting et al. But the other way is to augment it with factual information retrieved from the internet, right? So for smaller models, if you increase the context window while training, that automatically does make them a bit big. So they no more remain small because you need more compute to train them. So you would like to expand the context of a model without relying too much on the capacity of the model weights to interpret those prompts. So in chain of thought, at the end of the day, it's you who are providing the prompts in your way of English and hoping that the model will understand it. But I believe that if you simply scrape off paragraphs from the internet, it has less randomness and less human specificity, so to speak. So I would still go with retrieval and then think of if it solves my task. So is that what you were asking?
Yeah, I guess I was just wondering whether if you expand the context window, you can rely less on choosing the right context to put in.
Not sure I understand that, but yeah, like increasing the context window increases the complexity of training these models. So I would imagine that might not it might not be comparable if we increase the context window.
Okay, thank you.
For the same model. Yeah. And someone else has asked, can we convert causal LM models to masked LM? So I think you're trying to ask if decoder-only models like GPT can be compared with masked LM models like BERT, right? So I would say, like, if you look at this paper, here we have a lot of things going on with masked LM modeling and how you're jointly training autoregressive models with encoder only models. So it's like encoder only models, decoder only models. How do you bring that synergy between them? And I think that's what you're pointing to. But I don't think there's a way of conversion. At least I am not sure if that is possible or that makes sense. But if anyone else has any thoughts, please feel free to add your inputs. So I am not very well aware of the work in UL2. All I know is that it's able to do COT, but with a lot less number of parameters, which is like 20 billion. Could you tell me more about it? And I'm happy to have a discussion.
Yeah, sure. So yeah, I have found that they can do like even the flan, like the T5, which is 11 billion, and the COT can do those, a little bit of it. Mm-hmm. That's pretty much all. And I think it's because they're trained on like instruction tuned models, right? So they're following instructions. So let's think step by step is probably one of the instructions that was written.
But again, like the thing with instruction tuning is that, as you saw, there was a paper I mentioned on COT not working for ChatGPT, right? So I am a bit wary of whether these two methods are synergistic and that they can be combined. But I'll take this up offline and think about it.
Right.
I mean, for now, I don't.
Depends on what. Yeah, it depends on the data set and how you're writing it. So yes, I do agree.
Yeah.
Yeah. Any other questions? Okay, then I think we should end here. Thank you, Gargi, for sharing your expertise and knowledge with us. How long did it take for you to get to be an expert of this topic?
Well, who knows? I'm an expert. Maybe I've just a few shotted myself with these papers.
How long did it for you to prepare this talk?
I spent like 3 or 4 days, I'd say. Yeah, and I think it's a nice time to be on Twitter because every now and then something new comes up in this field, especially. So do keep scrolling on Twitter and be updated.
Yeah. Cool. Thank you. Keep in touch.
Yes. Bye, everyone. Thanks, Roseanne.
Thank you. Great talk.
Thank you.